Okay, so we're going to answer the question of whether flow inside a mammalian cell can be treated as a continuum fluid mechanics model. Question, therefore, is how many molecules are really inside a inside a mammalian cell? Are there going to be a lot of molecules, or is it only going to be a small number of molecules? If it's only a small number of molecules, then we cannot treat it as continuum fluid mechanics. That would suggest that the number of the intermolecular distances are going to be comparable in size to the size of that cell. First thing we're going to do is just calculate the volume of the cell. We know that it's roughly it is a sphere, and we know its diameter is 10 microns. So we have that 10 microns, and we're going to turn that into a radius by dividing it by 2, and then we're going to cube that and multiply it by 4/3 pi. So that's 4/3 pi r cubed gives us our volume. And that easily gives us a cell volume of 5.235 times 10 to the minus 25 meters cubed. So this is truly a small thing, obviously. 5.235 times 10 to the minus 25 is a very small volume. And that's what the volume is of that cell. We know the density of water. Water density, as I encourage you to remember, is 1,000 kilograms per meter cubed. Really is pretty constant under a variety of conditions. So the mass of water in that cell, therefore, is simply the density times the cell volume, and that gives you a mass of water of 5.23 times 10 to the minus 22 kilograms. So easy math, it's 5.235 times 10 to the minus 25 times 1,000 gives me 5.235 times 10 to the minus 22. So that's the mass of the water. Again, very, very tiny. How many molecules is that? Well, in order to know that, I have to figure out what the molecular mass of water is. Well, the molecular weight of water for water, the big M here, referring to molecular weight, is 18 grams per mole. So I've got to be a little bit careful, use grams and moles or kilograms and kilomoles. I'm going to use grams and moles. And so then I'm going to be able to calculate how many molecules are actually in that cell. And so M of moles in cell, the moles in cell is 5.235 times 10 to the minus 19 grams. So I've converted the kilograms to grams divided by 18 grams per mole. And that's going to give me the total number of moles. And that comes out to be roughly 2.91 times 10 to the minus 20 moles. So I have 2.91 times 10 to the minus 20 moles of water. And how many molecules is that? Well, I know that 1 mole of water is equal to 6.022 times 10 to the 23rd molecules. So that's how many molecules are in a mole. So the number of molecules in my cell of water is roughly 6.022 times 10 to the 23rd times 10 to the 23rd times 2.91 times 10 to the negative 20 gives me an answer of roughly 17,500 molecules. So I have 17,500 molecules inside a single mammalian cell. That's a lot. That's going to be enough for me to say I think that's going to be continuum mechanics. We can deal with this as continuum fluid mechanics. I have 17,000 molecules in that space. So we're okay with this. You could calculate intermolecular distances if you wanted to, but you really, I guess you could imagine a flow feature inside the cell that would not be continuum mechanics. For instance, if you were going to study flow around an individual protein or something, that would not probably be continuum fluid mechanics, because that would be a feature inside the cell that's at the molecular level. But the cell itself has a large number of molecules, and so when we're talking about flow in and out of the cell, flow through the cellular membrane, the continuum mechanics model seems reasonable since we have a very large number of molecules in there. Okay.